Sir, good evening, sir. Shall we start, sir?
Yeah, please.
Yes, sir. Thank you, sir.
Thank you.
Very good evening to one and all, and I welcome to day 5, session 5 of FDP. I, Pawan Kumar, working as Assistant Professor in Department of Mechanical Engineering, BITM Bellary, take the privilege to introduce our today's speaker, Dr. Ishwar Prasad, who is working as Assistant Professor in Department of Metallurgical Engineering, IIT Indore, will deliver the talk on microstructural aspects of additively manufactured alloys and their mechanical properties. Sir has pursued BTech from NIT Warangal and achieved first rank, master's degree and doctoral degree from IISc Bangalore, and also postdoctorate fellowship in Hopkins Extreme Materials Institute from Johns Hopkins University, Baltimore, USA, and received MHRD fellowship from Government of India. He has served in TVS industry for 2 years and got the teaching experience of 16 years. His service to academia as a reviewer has contributed in 22 journals and got 1,552 citations with 24 journal publications. His professional achievements are in various zones as Associate Dean Academic, Review Committee, Guest Scientist for Germany and France, Visiting Faculty for Xi'an Jitong University in China, and Invited Speaker for International Conference in China, and also listed in 33rd and 35th editions of Marquis Who's Who in World. Sir is also the convener for various selection committee, symposium, conferences, and workshop on R&D at IIT Indore. Sir was also the coordinator for QIP, TCube, and guest editor for Materials Today Proceedings and MOM Special Edition, and board member for Indian Council, Executive and Curriculum Committee member also. Thank you, sir. Thank you for accepting our the request and delivering the session today. And I welcome you, sir.
Yeah, thank you, Pawanji. Thank you for the generous introduction. I really appreciate your efforts in doing that. First of all, I would like to thank you and other organizing committee members, especially Raghavendra ji, who's been coordinating the event from the beginning, along with your colleagues. So yeah, it's my privilege. In fact, I feel honored to be giving this talk. This lecture on ATAL FDP. So the topic of my topic today is microstructural aspects of additive manufacturing alloys and their mechanical properties. For the past 2 days, probably for the past 4 days, what you would have seen with starting Professor Pandey from IIT Delhi, commonly Professor from IIT Delhi, you would have seen about the various aspects of additive manufacturing, the technological aspects, of the mechanical engineering aspects, like how to build the machines and how the functions and so on and so forth. So what I slightly do is that I'll actually emphasize today's next 2 hours on the microstructural aspects of additive manufacturing alloys and their mechanical properties. Since our group works in mechanical behavior of materials, we are interested in how this structure influences the mechanical property. That is what our emphasis is. Yeah. Sorry. Yeah. Next slide. Yeah. So if you look at any the holy grail of materials engineering, so this is called as materials tetrahedron. What you're seeing is the materials tetrahedron here. So the tetrahedron, each corner of the tetrahedron actually indicates an indicator. Let's say performance, properties, structure, and processing, right? So if you need a performance of a vehicle, let's say you want taking automobile vehicle, which requires a very high power engine. So okay, it requires certain properties. Okay, it requires very high temperature stability or high strength and so on and so forth. So for that, the strength indirectly is controlled by the microstructure. What is the internal microstructure of the material, which we will see in the next slide. And then again, this microstructure can be tailored by the processing. Okay, this is where we are talking about additive manufacturing can play a vital role. Right? Conventionally, we know the way you would have seen your many of you must be teaching your material science course and manufacturing course in your schools. So where we see that the casting, rod processing like forging, rolling, and extrusion, these are the standard processes that are available to make the materials, right? So we'll also see sort of that comes under subtractive manufacturing, So thus process are well established or a decade or a century, then how do you control the microstructure of this I mean, by altering certain heat treatment and certain temperature, strain rate, and so on and so forth. But additive manufacturing, what you're doing is that you're directly making the finished component, unlike the subtractive manufacturing. So it's important to have a very good understanding about how the processing parameters in additive manufacturing influences the microstructure. Okay, so that's what I'm talking about. So the structure could be, I'm talking in terms of mechanical properties, it could be functional properties as well. When I say functional properties, it could be electrical conductivity or semiconducting properties and so on and so forth, right? So again, the microstructure, when we say microstructure at different length scales. What I mean to length scale is that you can see the micro grains with your eyes, and you can also see the micro grains. I mean, the grains are a few atoms when you go to very high resolution experimental techniques. Let's say what I mean to say is that when I say microstructure, so the objective of materials engineers to get a broad hold of this understanding this tetrad, your job is done. Typically, who are the mechanical engineers or material science engineers or design engineers, they always get I mean, they want to have a detailed what is that hold on this this materials tetrad. They'll be able to design new material and so on and so forth. Okay. So if we look at the intrinsic length scales of the material, so I'm talking about let's say you're talking about an Audi or a car here, or like a Porsche here, and then you talk about the cylinder block or cylinder head or crank casing or whatever different components you can take it out of it. So this is what typically you look at in a macroscopic sense, right? So when I say dig deeper into a small region of this vehicle of this component, engine component, and then look at this under an optical microscope by using certain operations called metallographic sample preparation, and then which involves polishing and then followed by etching. What you see is that you see different features which you could not see with the naked eye, right? So these features includes grains, grain boundaries, and so on and so forth. These white regions are called grains, and which are separated by dark regions, which are called grain boundaries. Okay, so what you can see is that you can see grains of different size, different dimensions, whereas a grain boundary is a different nature as well, which you cannot distinguish here, but still there are techniques which you can be able to do that. So what at semblance, what looks like is everything is same. All the grains are same and everything is same, right? So if you look at the bar here, the micron bar here, it is actually 20 microns we're talking about, right? The scale bar, what you see here is that it is 20 microns. So if you dig deeper into further and technique called as scanning electron microscope, what you can see is that, so you got down from 20 microns to 2 microns here, the features, and actually I magnified a small region of this optical microscope. What you can see is that all grains are not same. Okay, some grains are darker, some grains are lighter, and some grains are grayish in shade. Right? So what it sees that each grain has a different character. What you cannot see with optical microscope, you could be able to see that with a scanning electron microscope. If you further dig deeper into a small region of this, and other features what you can see apart from this different colored grains, is that you can also see that there are certain particles which are actually embedded in the material, okay, which are deliberately added to improve certain properties in the materials. We'll talk about in the next slide. So if again further dig deeper into that, and then what I'm talking about is I coming down from 2 microns to 500 nanometers, which is one order of magnitude lower than that. What I can see is that I can see a boundary here, a clear grain boundary, and I can also see certain features here, which are very important feature for mechanical properties called as dislocations, which are one-dimensional defects in materials. And the dislocations will come and then they can actually get blocked at the boundary to enhance the strength of the material. That is called as grain boundary strengthening mechanism. Okay. What you can further see is that there is a certain these boundaries are still there are the particles actually grown bigger and bigger. So what I'm talking about is not bigger and bigger. So you're actually magnifying the zone. That's why you could be able to see a bigger size of particles. Okay. So this is actually taken from a technique called transmission electron microscope. If I further dig deeper into a small region of this, right, I can see the particles, the individual atomic particles. And if you look at the micron scale bar here, I came down by 2 orders of magnitude. I came from 500 nanometers to 2 nanometers. Right? So what I can see is that I can see individual atoms in the material. So nutshell, what I want to say is that whatever you're adding in the alloying elements, let's say you're adding nickel in stainless steel, you're adding nickel and chromium to a steel, right? What does the nickel do? Right? Nickel increases the strength of the material, or chromium increases the corrosion resistance of the material. What exactly they do is actually they can sit inside a certain specific regions of the particle of the structure, and they improve the certain mechanical properties. Right? So if you look at it, there are no techniques that are available to understand what exactly happens at atomic level and below submicron level or subatomic level. So what we seek is that we seek the help of typical computational experiments. What I'm talking about simulations like density functional theory or molecular dynamic simulations to feed it into the experiments. Okay, this is what I'm talking about, the microstructural length scales in the material. Again, remember we are talking about material structure intimately can be controlled by the processes, which in turn affects the properties and vis-a-vis the performance of the material. Right? So if you look at it here, so key descriptors of a structural material, if we take it, so there are stiffness, strength, and toughness. Okay, these are the three important properties what we always work on, right? All the mechanical engineers or design engineers, they work on, they want to increase the strength of the material, and also they want to increase the toughness of the material. Right? Say toughness means if talking about any critical component is there, and you want toughness, the fracture toughness, the toughness to be very high for the component. Let's say you talk about a typical concrete pillar, you don't require toughness, and require very high strength for that, right? So it doesn't exhibit any plasticity here. So in conventional materials, there is enough of theories that have been proposed, enough of work has been done to understand how do you improve the strength and how do you improve the toughness. Again, this is done by processing, certain processing method. Let's say what I'm talking about is this could be a strain hardening, and you take a material, you beat it to extensively, and then it becomes harder and harder. Okay? That is called strain hardening. So what I'm saying is that this you cannot do with the additively manufactured alloys right now, because you're directly making the component at the end component. And then that's why you have to tweak in how can you incorporate these kind of strengthening mechanisms to additively manufactured alloys is a critical problem people are working at right now. And grain boundary strengthening, as I told you before, as I shown you before, to increase the decrease the grain size will impede the motion of these dislocations and reduces the strength of the material. You put, I mean, you take a, that's where the nanocrystalline materials become very popular, because you take a microcrystalline and millimeter or nanocrystalline materials. In nanocrystalline materials, what happens is that you have large number of grain boundaries for a given area, and these grain boundaries will impede the dislocations. That's why they increase the strength of the materials. That's a typical grain boundary strengthening. Most of you would have heard about this Hall pitch strengthening. It is also another term that is being coined for grain boundary strengthening. And solid solution strengthening, this is what you're talking about. So let's say you add certain alloying elements, and these alloying elements deliberately get seated to certain places, which is again processed by kind of rod processing or heat treatment processes. So, and then you can increase the strength of the material, right? That's what typically do it in a this is conventional subtractive manufacturing components. So where actually you do all these operations, at the end you machine it to make a finished product, right? Whereas in additive manufacturing, you start with the product, so you cannot be able to do it any of this, except that, I mean, people are working on how do you incorporate it by certain hot pressing methods or heat treatment methods. How can you post process these additively manufactured products to improve these properties and so on and so forth. And precipitation strengthening, I mean, as I showed you before in the previous slide, so there are some small particles that are embedded in the microstructure. These are called as precipitates. These precipitates also will be helpful in increasing the strength of the material. So one advantage with the precipitation strengthening compared to other methods is that precipitation strengthening, in addition to the strength, it also improves the ductility of the material. So that's an advantage with the precipitation strength of materials. And then you talk about dispersion strengthening is another mechanism, which mostly the people working in dynamic energy, they use it. And this is called texture hardening. This is another mechanism by which the strength of the material is improved. Okay, so what I mean to say is that, so these are the methods that are being in practice for more than century, right? So more than century, how can you increase the strength of the material, even though the mechanism is being understood lately. But So this is what actually these are done. All these process methods, what I've done, what I told you before, it's been done before making the final component itself. Right? So you look at, this is what I'm talking about, the flow. So you're talking about process flow of subtractive manufacturing. This SM stands for subtractive manufacturing. And you have melting and casting of the alloy, and you have a rod processing. This rod processing also a very important processing step in a subtractive manufacturing method, which we'll discuss a couple of a few slides on this as well to set the ground for what are the challenges that are being faced by people working on additive manufacturing processes. And then people do is additive heat treatment. After rod processing, we do heat treatment. Most of you would have been seen this normalizing, annealing, and so on and so forth. All these called as heat treatment processes. And followed by you machine the component to desired shape, and then the finishing operation. The finishing operations could be shock peening and so on and so forth, or any other painting and coating or what. So if you go back to additive manufacturing, it's completely the most important part here in the powder making. We'll stress upon something on powder making today's lecture. And powder making is a very important process which dictates the quality of your additive manufactured product. Okay, that's important. And then once you make the powder, you directly making the 3D finished component. Okay, you are avoiding all these steps. Especially the most important step is the rod processing step, which is where you homogenize the metal there. Okay, that is what you are trying to avoid. So 3D printing. So you do this. Yeah. So you in 3D print, what you do is actually you make the final component using certain processing methods, which we'll stress upon subsequently. I mean, probably in the past 2 days, we've been looking at SLM, E-beam, DED, other techniques. Selective laser melting, electron beam melting, direct energy deposition, and so on and so forth, followed by your finishing operation. Okay, so you're eliminating all these 3 important steps and putting in one this. Okay, then the traditional understanding whatever we have, how can you translate that understanding to this additive manufacturing is any challenging process. Okay, so yeah, so what I want to say is that if you look at the subtractive manufacturing, there are standard thermomechanical processing windows have been developed. Okay, so I'll also briefly touch upon what are these processing windows in the subsequent slides. So what I'm talking about is that this has been in practice for quite a long time. Okay, to obtain the desired microstructure. This is very important actually, to obtain the desired microstructure. So uh, unlike your other materials, additive manufacturing material, right? So which actually declares the mechanical properties. And most of the AM studies again are focused obtaining the microstructure only similar to wrought alloys, because whatever happens is that whenever you are trying to convince an aerospace engineer or something, you say that the microstructure what you are looking in the subtractive manufacturing, uh, the whatever you made through additive manufacturing is similar to that of subtractive manufacturing, then there is a chance of convincing them. Okay, despite that, there are certain towards the end, if time permits, we'll see a case study by aerospace industry where we see that there is a critical, even people are not trusting some of the subtractive manufacturing products because still there are many things to be understanding in that. Okay, so commercial industries are very conservative, hence they do not take risk directly replacing these wrought alloys with the AM alloys. Okay, that's what the problem is. We'll see at the end, will time limits. Okay, the most important component, if you look at it here, the conventional manufacturing methods like casting, bulk manufacturing methods like casting, look at the cooling rates. Whenever you take to the liquid metal and then try to cool it down to room temperature, the kind of temperature rate at which you cool are very low. In fact, at 10 power 0 to 10 power 2, 100 K per second, which is actually uh, uh, pretty low. Right. So the moment you compare the cooling rates with additively manufactured processes, you're talking about 5 into 10 power 5 to 10 power 6. Okay, you're talking about 4 orders of higher cooling rate. Okay, so what happens is that whenever you cool the material, so let me just have next slide actually. Yeah, so this is what I'm talking about. Whenever you cool the material at slow cooling rates, right? So you develop this kind of dendritic structure. Okay, it is like a difference between a slow cooking and fast cooking. Okay, in slow cooking, what happens is that you're actually under equilibrium conditions. The whatever you're cooking actually it soaks up well. Whereas in high cooking, you don't soak up well. The surface gets softer and the core still gets harder. Okay. So what happens is that whenever you're cooling a material, you have to ensure that actually the temperature is uniform, is uniformly cooled entire temperature, so that the properties what you're looking at here, 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 here should be the same. Okay, that's what the objective of any engineer. So since the casting it is not allowed, it's not happened because of the cooling rates or whatnot, even because of the cooling rates of 10 power 2, right? So you generally do a process called rod processing. Okay, the rod processing could be forging operation, what you typically see in a industry. Probably I think you're going to visit Jindal as well. I've seen the your one of the schedules in the next week. So there you tend to look at many of these forging operations or rod processing operations of the steels, right? And then rolling operation, which most of you know, where you take the material to high temperatures in both the cases, and then forge it or roll it to obtain the desired microstructure. So then the problem is that how high the temperature, what is the temperature I need to heat it, and what rate I should do this forging operation, at what rate I should press it. These two are very important operations which you talk about in the next slide. So again, similarly, the rolls rate, at what rate I should move the rolls, and what the temperature of this billet that is being put into the roll between the rolls. That's another important parameters that actually thermomechanical processing gives us. Right, and what are the optimum processing conditions? Are there any rules for the traditional manufacturing, subtractive manufacturing methods, conventional manufacturing methods? Again, extrusion, most of you know about it. You're talking to put a it's the way what we do every day. We take the toothpaste out of our toothpaste tube, where you do an extrusion operation to take the paste out, right? That's a typical extrusion operations. Instead of paste, you put a extremely heavily soft metal, and then high temperature you press it, so you're going to get this extruded part out. Okay, that is a typical extrusion process. So if you look at it, what happens is that what are the optimum processing methods? What I'm talking about is I'm setting a tone for what are the different microstructures that you see in a traditional manufacturing route, and how these are actually comparable to the additive manufacturing routes you're trying to look at now. I'm trying to I'm pitching like that. If you look at what are the processing maps, okay, there are certain rules that are there to obtain desired microstructure by conventional manufacturing methods. Okay, when I say subtractive manufacturing. So these are called as processing maps. Okay, the two most important parameters that people use in rod processing route are the rate at which you are rolling or forging the material, and the temperature at which you are putting the billet. These two are the important parameters. Okay, so people had, especially Professor Bhavya Prasad from former IIC, a professor, he made certain rules to understand what are the optimum temperature and strain rates for rod processing methods. So rod processing, typically what I'm talking about here. So you're taking a forged billet, you're taking a high temperature, I mean, you're taking a certain component, you're making it to this shape by using a closed die forging. Right? This is what actually you know as closed die forging. So at what temperature, if the steel, if this is a steel, what temperature I should forge? Let's say it should be 1000 is enough, or 2000 is enough, or 1200 is enough. Which temperature I should be forging? 2000 root there's a melting temperature, beyond the liquidus temperature. I'm talking about 1200 or 1500. Which temperature I should forge? Okay. Similarly, what rate I should forge? At what velocity I should hit this? Okay. The velocity is one way relation to the strain rate. The velocity is by length of the component that gives you the strain rate. Velocity and strain rate are analogous to each other. Okay. Typically, what people do is that people constructed certain maps using some dynamic materials modeling maps to arrive at a rules. What is the optimum temperature and what is the optimum strain rate that a material should be deformed or rod process, so that to arrive at a desired microstructure. Okay. So look at it here. So what people do is actually you take a small sample, a piece of sample like this, and then you deform the sample at different temperatures. Let's say these are temperature 200, 250, 300, 350, 400, 450, 500, 550, and 600. These are different temperature rates. You're trying to do that. And then these are the different strain rates. This corresponds to certain velocity. Okay, V1, V2, V3. These are different velocities with increasing order velocity here. So what happens is that when you do that, you generally materials tend to exhibit a property called a strain rate sensitivity, called strain rate sensitivity. Okay. What it does is actually the moment you are increasing the hitting rate, the materials exhibit a higher flow stress. Okay, because of the character of the dislocations, that is what the mechanisms tell us. So what happens is that if you given temperature at a given temperature, so if you are increasing the velocity, your flow stress goes up. Okay, the flow stress is increasing with strain rate. Sigma increases as epsilon dot increases. Epsilon dot means velocity I'm talking. Okay. So what Professor Prasad has done is actually Prasad has derived computed by from the dynamic material modeling. I'm not going to much deeper into that. So he found out what is the efficiency of the power dissipation. Okay, if you talk about any method, any process, what happens is that some of it, whenever you do a process, some of the energy the material gets absorbs, and some actually dissipates to the surroundings. Okay, so the one that is absorbed by the material will be consumed in the microstructural changes. We will see what are the microstructural changes in the next subsequent slides. And then the ones which actually goes to the heat, I mean, is unused energy. That's the energy that is we are actually unnecessarily putting it. Okay, so but energy of the process is pretty. I mean, you're talking about the best process energy is 20% or 30% efficiencies. 80 or 70% goes as a heat to the surroundings itself. So what I'm talking about is that, so based on the strain rate sensitivity, which is called as dou ln sigma by dou ln epsilon dot. Okay, otherwise delta sigma by delta epsilon. Okay, which is what I'm talking about here. Okay, so that gives you the strain rate of the material. So this is the delta sigma, and this is your delta epsilon dot. So that gives you the strain rate sensitivity of the material. From the strain rate sensitivity, you should be able to calculate what is the energy of power dissipation. How much of the energy the material has dissipated. If it is actually dissipated more to the surroundings, it is actually consumed within itself is more. That is actually consumes more. Actually, it actually changes in the internal microstructural changes, which you will see in the next slide. Similarly, there are certain uh, instability parameters. So, which I'm talking about, efficiency power dissipation is one thing. And what are the changes that material takes place when it consumes this energy? It could be a good change, or it could be a bad change as well. Okay, if it is a change for a good, so it gives you a very homogeneous microstructure. If it is a bad for a change, it gives you very heterogeneous microstructure. So what happens is that similarly you do power dissipation map. Generally, what you can generate these maps, and there are ASM handbook is also available on this. And then this power dissipation map, and then also that you can actually generate a map called instability map. You superimpose one on top of each other, and then you get this kind of processing map. Okay, so what this processing map will tell you, okay, this is actually a very simple concept. You don't have to worry too much on this. So what happens is that if your temperature is this, and if your strain rate is this, okay, this is the range of temperature, and this is the range of strain rates I'm working, or velocities I'm working. Then what happens is that you'll get a very good microstructure in the material. Okay, what I'll show you what is good microstructure, what is bad microstructure in the next slide. So suppose your temperature is this, your strain rate is this. Okay, this is your window. Then you get a very bad microstructure. Bad microstructure is that the material properties are highly non-uniform. Okay, you don't want any operation to be carried out in this design. Okay, so anybody who makes any new material, the first thing they do is actually create this map, construct this map, right? Construct this map, and then you forge it, roll it, or extrude it accordingly only in this region. Okay? You avoid on entire region. You avoid this entire region. So this is what exactly people have been doing for the centuries on the subtractive manufacturing method. So typically, so this is what actually I'm talking about. This is what you're trying to avoid it. Let me go back in detail. What is when you do a process in this region, how does the microstructure look like? And when you do operation in this look like, how does the microstructure look like? The difference in microstructure between this and this region. If you look at it here, stable and unstable mechanism I'm talking about. So this is one such processing map that is developed for a AZ31 alloy. Okay, AZ31 is a magnesium, aluminum, zinc alloy. It is a magnesium, 3% aluminum and 1% zinc. Okay. So when you do this processing operation, this is the instability zone. Okay, you want to avoid operating in this zone. You don't want to avoid this. You can do it here, you can do it here, you cannot do it here, you can do it here, you can do it here. Okay, so I'm talking about this is the temperature strain rate window you can operate. What happens is that let's take one such alloy, AZ31 alloy. So I'm actually doing this operation at 350, 350 and 550 degrees centigrade. Two temperatures and another temperature. 350 degrees centigrade. At 350 degrees centigrade, I'm using at a two different velocities. I'm striking this sample what I kept in that material. Okay, in between the two anvils. So when you do that at 0.001 at domain 1, you get a microstructure like this. I'm pretty sure you'll be able to see this microstructure. You see a very homogeneous grains. So all the grains are actually of equilibrium, equisized grains. Okay. The grain size is slightly bigger. We talk about 20 microns here. Grain size is slightly bigger, but you get a very homogenized grain shape. Okay, and you do it at a 10 as well at high rates, and then you get a similar grain size, but I mean you get a very good microstructure here too, but slightly smaller grain size compared to this this operation. Slightly increase the temperature, you get a very fine grain size. Okay. If you look at the strength wise, this gives you the best strength compared to these two, and this gives you lowest strength in these three two. Okay, this is called as dynamic recrystallization mechanism. Okay, there is a way I'm saying this. I don't get confused because so I wanted to start with additive manufacturing, but I want to set the tone for AM. That's why I'm actually doing all this. Okay, so when you do this unstable mechanism, these are the desirable microstructures you need. Okay, so in a conventional setup, in a subtractive manufacturing setup, you have known the rules for centuries and what temperature you have to work, at what strain rate you have to work, so that to arrive at a desired microstructure. Okay, so basically the person who's working shop floor, right, he only knows, okay, I need to operate at this temperature at this strain rate, but why he does have to operate that temperature, this is what actually this will tell us. Okay, these are the ones which tell us why he has to operate that particular temperature range or strain rate range. Okay, so if you look at it here, undesirable microstructure, let's say I've taken another material which I'm operating on this zone or in this zone. So what I get is a microstructure like this. The same material, if you are doing it in a domain or good domain or domain which is free from unstable regions, you get a very good microstructure. You're talking about domain which is falls in the instability zone, you get microstructure like this. Okay. Similarly, you get a microstructure like this in this domain. Okay, very high rates or something. Okay, these are very undesirable microstructures. Okay, you don't want any of your engineering component to have this, right? So that these are the typically most of us who working in this failure analysis part, many people approach us that, okay, I actually got the sample failed. Why this is failed? First thing what we look at is that we look at the microstructure, initial microstructure. And when we see very uniform microstructure, we say that it could be a design problem, it could be a overload problem or something. But the moment we see any of these undesirable microstructural features in the sample, we say that while processing this material, there's something would have happened. Okay, something which we don't know, but I mean, this is what the reason. So there are regions where the material has certain pores or certain wedge crackings or certain adiabatic shear bands or certain flow localizations. So the initial processing of the material is not good. So when I say processing, it could be rot processing or it could be cast processing. And then you have to change the entire batch. Otherwise, it's not no longer sustain. The metal can sustain. Okay, so these are all the undesirable mechanisms you want to avoid it whenever you process it. Okay, that is the reason you have to optimize the temperature and time space so that you will get a desirable microstructure. Similarly, another example, we're talking about 304 stainless steel, right? So this is the processing map for 304 stainless steel, and this is what unstable zone. So you want to avoid this zone, and you want to process in this region. Let's take I take four different samples A, B, C, D, which corresponds to different temperature and RAM speeds. Okay, RAM speeds is nothing but the strain rate I'm talking about. RAM speed is here, or RAM speed. Okay. A, B, C, D here, both are of the same initial dimensions. If you look at the surface here and surface here, okay, this surface is very rough. This is very smooth. Okay. The only difference is that you process this at 1080 and 1090. Both are the same temperatures, more or less 1080 and 1090, more or less same temperatures. Look at the rates. This half of the strain rate what you're using it. Okay, if it's doing it 300 rams per mm per second, you're pushing it, whereas 150 mm per second you are actually pushing it. You are decrease the rate by keeping some temperatures same for both of them. Right? You get a completely different structure response. Right? Very rough surface. Right? Very rough surface, which is undesirable for any engineer to look into it, because it actually creates a lot of fatigue problems. I think Professor Jayaganthan would have discussed about you what is the fatigue of additive manufacturing alloys yesterday. Whenever you see any surface roughness, right, especially if you don't, even the additive manufacturing product, if you don't properly treat the surface, you're going to end up in very poor fatigue properties. Okay, whereas this the one which you processed it actually gives you a better microstructure. Okay, so this comes down to what are the challenges ahead. So in traditional methods, in a nutshell, you have a very sound processing methods. You don't know at what temperatures you want to operate, at what strain rates you want to press, at what velocities you have to compress the specimen to make the component. They're all properly laid. The rules are pretty laid. So do we have such a rules for additively manufactured products? Okay. Since we know that you're directly avoiding all these steps and you're reaching the end product in a one go, right? You're avoiding all these methods. I'm talking about processing method. So what are the microstructures you get it? Okay, is it desirable or undesirable? Okay, otherwise, can we develop a processing map for additively manufactured products? Okay. So in conventional subtractive manufacturing, you have temperature, you have strain rate to tweak what in between those two to get the microstructure. But in processing in additively manufacturing process, you don't have any of those, right? What you ideally have is that you have a bunch of parameters I'm going to talk about in the next slide. So those parameters you have to tweak it. Those unless you optimize or properly optimize those parameters, you will not be able to get a desirable microstructure. So once you will not get a desirable microstructure, your properties are not going to be good, and your properties are not going to good, your performance of this additively manufactured component cannot be on par with the subtractively manufactured product. Okay, that's very important, right? So is it possible to obtain, again, with all these controlling the processing parameters, is it possible to obtain a microstructure which is comparable to the raw processed ones? So first of all, it could be better than, because I think, I mean, we have seen in certain Inconel 718 alloys, right? Some additively manufactured product at the laboratory scale, it does perform much better than the conventional subtractive manufactured products, right? But actually, first thing is that you have to convince the people who are end users, saying that okay, this microstructure and this microstructure are on par with each other. So I think, I mean, otherwise, at least to start with, and then if it does better, I think you can actually tomorrow. Sometimes whatever happens the laboratory scale may not be able to applicable for I mean a full length scale, because it's the concept of similitude may not be able to apply to all the properties or something. Okay, so what I'm talking about is a comprehensive understanding of the role of various process parameters on the microstructure is extremely a key to if you want AM to be in a applied in a engineering component. I'm sure Ram Prabhu tomorrow, Dr. Ram will touch upon a lot of these components and defense applications tomorrow. So he's going to stress upon some of the applications what are needed and what are the AM processes that they use. Okay, for any process, as I told, the key is the microstructure. Okay, so if there are any questions I would like to take, and then probably we can. Pavanji, how are you setting up? We'll finish the presentation and take a check it.
Yes, sir. We can take like that, sir. After finishing the session, we can take the question.
Okay, that's right. That's right. Then actually, I'll we have 20 more minutes session. I think we'll talk 10 more minutes. I think. Okay, so you talk about the AM processes. So actually, this is the typically if you classify that. So you have powder bed fusion processes where SLM and EBM are popularly used, and you have a direct energy deposition. DED. DED uses both wire and feedstock, and BED also can use laser and E-beam. So both you can use it. And another process is called as binder jet printing, which is BJP analogous to, which is actually infiltration consolidation. BJP is also coming, binder jet printing is also becoming more and more popular now. HP is investing a lot on this. And you have a sheet lamination. This is ultrasonic additive manufacturing. This is, I mean, probably most of the people who are working in welding might be aware of this word. Okay, so what I'm talking about is for this presentation, I'm going to talk mostly on this powder bed fusion and some of the SLM process, which looks pretty promising in terms of commercial applications. And other processes also are important, but I mean they also fall under these two I'm talking about. So powder bed fusion, and there are certain ASTM standards that are developed to understand different process parameters and different nomenclature that is given to each of these processes. So if you look at the SLM process, I mean, probably you would have been seeing this in the last couple of days. So here, what you're talking about is that initially this is what the material inline with. So what you're doing is that there is a rake, a rotator arm. This rotating arm spreads the powder onto this, and then there is a CAD model you already fed into the machine. That CAD model gives you certain shape to the as a result of your SLM operation. So what happens is that at what rate, at what thickness you are supplying, and what is the thickness, and what is the laser beam intensity, and what is the speeds, what is the spot size, what is the scanning parameters, scanning energy that is being put in. These are the parameters that are processing parameters in the SLM. And what is the particle size, particle distribution, particle surface toughness, right, and quality of the particles. And these are all actually the properties, parameters that actually affects the quality of the product as well. Right? And there is I mean, this is what actually you do this. This guy raises and this guy comes down. At the end, you get this end product. That is your selective laser melting. So in the E-beam, instead of laser, you use a electron beam. Okay. In electron beam, since an electron beam is very sensitive, you do it in a high vacuum process. And whereas DED you can do it with a wire fed or well as powder fed. Both of them actually are good. One advantage with DED is actually you can get a layers of different compositions, right? So since you are feeding it to the different wire feeds, you can increase the intensity of these, you can decrease the intensity of these, or you can you can increase the intensity of, you can actually tweak what that is advantage of the DED compared to the SLM and EBM. So more or less your powder composition, everything is fixed there. But DED, you are feeding it, so you can vary the functionally graded materials you can create with DED. Is very promising technique in that actually. DEDs. Okay. Coming down to the key process parameters. Look at it here. So these are the, let's say I'm talking about selective laser melting. Okay. So these can be classified. These are the typical process parameters. I mean, they can be many, but the most important ones are here. So the laser related, what is the scanning related, and the power related, powder related, and temperature related. Okay. So laser power, as I told, what is the laser you're using, how much power you're using in the laser, and what is the spot size. Okay, is the spot size which is actually being fed under that component, other in the bed, and what's the pulse duration. Okay, what is the laser pulse, It's a duration we are using it to to impinge on the sample. What is the frequency of the pulse? These are the 4 parameters related to laser. Let's look at the scan. Okay, scan speed. Okay, at what rate your skin? You're actually the scan is moving. That's important. And what is the hatch spacing? We'll talk about the hatch spacing subsequently. The hatch spacing between one layer to other layer. What is the hatch spacing you're giving? Especially when you do this island scanning, it happens actually. Hatch spacing. Between that, we'll see some of the microstructures based on the hatch spacing. How does a microstructure look like? And scan orientation. At what orientation you're doing the scan, like this or like this or like this. Okay, what orientation you're scanning, and also from this to this, how the scan rotation is varying. Okay, let's say I'm doing the scan like this, and then there is a scan like this, is called as 90-90. So let's say I'm doing a scan like this, I'm actually aiming at a certain inclined angle. That could be a different angle. Okay, the theta could be 90 or 67 or 50 or 45 and so on and so forth degrees. Scan strategy, we'll discuss about the scan strategy. There are several scan strategies are there, zigzag, island scanning and everything. We'll see that in subsequently. Powder size, and powder becomes a very important aspect of additive manufacture, because the quality of the powder dictates the quality of the product. These are all also important, but if they are good and the powder particles, the powder what you take is not of high quality, and then you're going to end up in certain problems in that. Okay, we will see that different powder particles and how they are manufactured and what are the quality and that subsequent slides. Okay, particle size. So what is the size of the particles? And size of the particles dictates what is the layer thickness you use. Powder layer thickness. Powder layer thickness is, so you are actually doing this layer thickness, right? So how thick the layer can be. Okay, if your powder particle size is 100 microns, okay, particle size is 100 microns, then your layer thickness should be some 10 times that of it, or 5 times that of it. Okay, so you can only create a very thick layers, but you cannot create very small finite layer thickness values. Okay, that also we'll see in the next slide. In particle size and distribution, particle size and distribution as well. What is the mean and what is the mean particle size, maximum particles, how closely they are distributed, and so on and so forth. What is the powder bed density, as I told? Okay, so powder bed is strongly, thickly dense or thick or thin. That also dictates what kind of end product you'll get it. And powder layer thickness. Okay, layer thickness becomes important process parameters as the powder quality. Quality of the powder. Quality of the powder could be surface roughness and then porosity and so on and so forth. Okay, so these are all important. And when talk about the temperature related process parameters, it could be powder bed temperature. Okay, what is the bed temperature? Because the bed temperature at the beginning of the next layer, when you're depositing it, if the temperature of this is very small, very low, then there will be a significant residual stresses that develop between these two. It leads to certain defects. We'll talk about that as well. Okay, especially I think Dr. Amit is going to talk about the heat flow and then fluid flow in additively manufactured products. I think he'll be stressing upon much on this hopefully in the next week. Okay, powder feeder temperature. What is the feeder? What are the feeder you're using it? What is the temperature of the feeder? Because if the temperature of the feeder comes down, whatever the heat you put it in, you have to heat the feeder. Otherwise, you can't put a cold powder on a hot plate. You're going to have some issues there as well. And uniformity in the temperature and temperature gradient. So what is the temperature uniformity in the plane? What is the temperature in the thickness, along the thickness, the gradient in the temperature? Okay, so these are all the ones which affects the key process parameters needed for additively manufactured product in a SLM process. Okay, so we talk about process parameters. Okay, these process parameters will affect certain end product. That could be the porosity. Okay, if you're whatever the process parameters discussed before, if they're not optimally used in the processing of these components, you're going to end up in porosity and you're going to end up in cracking, swelling, delamination. This is mostly happens when there is a differential thermal gradient between one layer to other layer, and the residual stresses as well. If the residual stresses also is another key problem in additively manufactured products components, that's why people do it in they have to anneal it to remove the residual stresses. And what is the substrate adherence and warping? That is another, the backplate, what you use dictates on what material, how easily you can pull it up the product that is that is deposited on that. And then these are certain microstructural controls that actually affects, let's say, material chemistry, melting and multiple geometry, solidification, microstructure evolution, cooling down, grain size orientation. We discussed about this. And thermal post-processing. What is the post-processing? You have to employ that. Okay. It could be heat treatment. Sometimes the people use a short cleaning followed by heat treatment. So those I'm talking about here. Because eventually they control the mechanical properties of the material. Okay. And feature stage and geometry of scaling. These are the important process parameters that affects the whether defects in the additive manufactured products or whether microstructural features in a AM components. Okay. Again, applied energy, beam interaction, heat transfer, process temperature. These are all. Okay. Okay. The feedstock and base plate. So I'll take up this feedstock and base plate and take a break. Probably I'll take questions, and after that we can again get started after 10 minutes or so. Okay. In feedstock and base plate, so in PBF, generally powder bed fusion uses pre-alloyed powders. Okay, while DED uses powder, wires, or feedstock. Okay, so as I told, one of the key advantages with DED is that since you're using powders of different, I mean, you can actually different hoses you're trying to put it. So you can actually, one layer you can put, let's say you're trying to deposit some aluminum and nickel component. Okay, let's say aluminum 80, nickel 20, you're doing it in the first layer. Second layer, you can do it aluminum 60, nickel 40. Third layer, you can do it aluminum 20, nickel 80. This you can do it in a DED process. Okay, functionally you can grade them. So what I'm talking about is that whenever you want to use very, I mean, hard surface for tough core and case hardened material, so you can actually employ this kind of technique into the. Okay, you have a microstructural, not compositionally, functionally graded components. You can use it in a DED process. Okay, so whereas in PBF process like SLM and DB, we don't have this provision. You have to use a same uniform border to build the component. Okay, that is typically we're talking about. Okay, quality of the AM component depends on the quality of the powder particles, particle shape, particle distribution, surface, as I told before. Okay, and build a base plate on which the powder is deposited provides. This build provides a thermal support because on which actually supporting. Sometimes what happens is that you're trying to deposit Ti64, titanium 6, aluminum 4, vanadium alloy, which is a workhorse in titanium aerospace material. So you have to use a stainless steel base plate, stainless steel base plate. Okay, so you can deposit. Otherwise, you deposit it another plate. It's very difficult for you to remove the component. Okay, that is also depends on what are the feedstock you're using, what component on alloy you're depositing. So correspondingly, you choose appropriate base plate. Okay, that is what typically people do it actually. Okay, it should be stable and it should rake out. Is what a rake out or rolling of the powder on the substrate. It should easily removable or something. Okay. I'll take a break here. I'll take questions, not break. I want to take questions and then probably we can move further.
Yes, sir. Sure, sir.
Yeah. Yeah.
Dear participants, now the stage is open for you. You can ask the questions to our speaker. Please unmute yourself and you can ask the questions.
Yeah.
Hello, dear participants.
Excuse me, sir.
Please, Professor.
Sir, among these three processes, what you have discussed in AM process, SLM, EB, AM, and DED, which is the most frequently used one?
So most frequently used one, all three are actually used. Mostly SLM is people are using it at a bulk component, laser one. Okay, that's what laser is the most popularly used technique, and
Hmm.
DED as well. Because
Okay.
DED also
So,
uses the laser as a source.
depends on the thickness or depend on the fast fabrication process we are going to decide, or what are the other parameters we are looking to while selecting the process?
Okay, it's actually as I told in DED, what you can do is DED is slightly inexpensive than SLM or SLM, because DED what you can use actually you can use also powder as well as a feedstock as a powder or wire as well. Okay, so using wire is the most. I mean, you don't have to powder making is a very expensive process. See, I mean, as I told, probably the past 2 days you would have had one of the bottlenecks in AM is that still the expensive. So especially the aerospace materials can actually actually spend some time because they don't have to sacrifice something on that. But
Okay.
what I'm talking about is that, so if DED is there, you can use a wide stock. The wide stock is easy to use it. We'll see what are the powder making processes. It's going to be a very expensive process. Powder making is.
Okay.
That's what people are trying to optimize how best we can get a good powders with a reasonably low cost.
Okay. So suppose if you go for SLM, that is the laser based. So which type of laser normally they will use, and what would be the power of the laser, sir?
Power on top of my head, I don't remember the numbers actually.
Okay.
Yeah.
Normal
I can get back to you.
normal gas laser
Yeah,
or
so you can see you can use an indic laser or something, but again it depends on what is your layer thickness.
okay.
Let's say my layer thickness is around 6. I think it's a. On top of my head, I remember. I think I have that laser. This one, I don't know whether I have it here, but I'll be able to share it with you.
Because
So
normally
typically,
the carbon dioxide laser is the most high power laser they will use. So such type of laser is required, or only a laser like helium neon or the NDIOG, this type of laser will also.
India is the what people use it to make a very precise SLM actually with it.
Okay.
India is what people use it actually.
Okay.
Yeah,
Okay.
but so that's what if you're. Yeah, because if you're using a very laboratory crude method, probably you can do it other laser. But if you're trying to make a component with precise dimension, then people will go for a India laser. I think that's what actually we also used in to make our TI-64 components.
Okay.
Actually.
How they are going to consider that heating effect? Suppose if you are using the laser, there will be some heating effect will be there. So how they are taken care of that, sir?
Heating effect of what?
When you use the laser for AM process, and definitely laser, because the laser has got some power, no? So that
The temperatures will go to
yeah,
almost around
temperature,
2000
yeah.
degrees centigrade as well. Actually, yeah,
Oh,
temperature goes to 2000 degrees centigrade.
uh,
And the temperature goes to very high. See, one advantage is that whatever the powder you're depositing, okay, the adjacent powder that is felt by this indic laser is actually you have to waste it as well. So what I'm talking about is, let's say, sorry.
but
Let me share this again. Yeah. So okay, yeah. So what you're saying is that, right? This
yeah.
one, right? So whatever you're saying is that you're putting the entire rake, the surrounding, whatever is there, right?
Yes, sir.
This powder you cannot use it.
Okay.
The heat felt by the powder, actually you have to get it waste only. That's a problem actually. In fact, that is why AIM is, though AIM say that is alternative method or something, but still cost is an issue here.
Okay. Okay, sir.
Cost an issue. But as you told, I think the temperature, especially when you're trying to optimize the temperature wise, still what I'm talking about is that still there are certain challenges which probably in the positive I'm not going to discuss, but especially the microstructure that you get in AM is completely different when you do it at high temperatures.
Okay.
So that you have to use certain post processing operations like post processing annealing treatments and heat treatments to avoid it, but still you're far from the microstructure that you get from the rot only. Yeah.
Oh.
Then,
Okay, sir. Thank you, sir. Thank you.
yeah, yeah.
Okay. Any other participants would like to ask the question? Sir, in fact, the session is very interesting.
Thank you, sponsor. Yeah. So the objective of me putting the subtractive manufacturing in processes is that because see, most of the probably the processing map concept, it is not being taught anywhere, and then many of the microstructural people who work in hardcore microstructures, especially for any industry. So first thing they have to do is that develop a processing map for the given material. Then only you tell them that these are the range of windows for temperature and strain rate windows. Then they'll be able to, process it in a forge or roll or whatnot, a roll condition or something. So that is actually typically is not still available for AM, but it may not be available for AM as well. So somehow the only thing what you can do is actually control these process parameters, like as we just discussing, Dr. Prasanna was asking. So the laser, what kind of laser we should be using? What is the laser energy intensity? What is the beam size or spot size? What is the scan speed, scan strategy? And these are things which you have to control. I think I'm going to talk about in the next subsequent slides in that case. Yeah.
Yes, sir.
Yeah.
Sure, sir.
Yeah. Yeah. We'll take 5 minutes break. Are any other questions are there?
Sure.
Yeah, please do.
5 minutes break. Sir, it's up to you, sir. If you want, we can take break for 5 minutes, sir.
Yeah, I think, yeah. We'll take another 5 minutes break and come back in that case.
Yes, sir. Thank you. Meanwhile, participants, we have enabled the chat box also. If you have any queries, you can please put a question in the chat box. We'll convey it to the sir.
Hello. Hello.
Yes, sir. Vijay Kumar.
Yeah, Vijay Kumar, sir. Sir, good evening, sir. It's a very wonderful presentation, sir.
Thank you,
Hello.
sir. Thank you, sir. Yeah, I'm audible. You're audible, sir. Please tell me.
Yes, sir. Is it audible, sir?
Yeah, you're audible, sir. You're audible. Please, please go ahead.
Hello. Yeah. May I speak? Sir, I am speaking to Professor Ishwar Prasad, no, sir?
Yes, yes,
Hello.
yes, yes.
Yeah, sir. It's a very nice presentation, sir. My question.
Vijayendra, sir, I hope the sound is not audible from your side, sir. If you want, you can just put a question in the chat box also, sir.
No, sir. No, sir. If I want to develop a composite of aluminum metal matrix composites, which falls under the category of wrought alloys, can we develop by using this FDM method, sir? Fused deposition modeling method, if it is in powder form.
I think there is some work being done in CSIR Bampuri Bhopal. They have not used silicon carbide, especially they are using graphene, a graphite product, and then trying to do some aluminum graphite based composites. Yeah, the properties looks promising. The properties looks promising, but still the specific properties look promising, but the absolute properties still there are certain issues.
Okay, just now you said, sir, with respect to AZ, that is the magnesium, no, sir, magnesium alloy, AZ31B.
Yeah, AZ31 alloy, AZ31B. Yes, yes, yes.
Yeah, my question is, we are one more thing we are looking for. My team we are looking for to develop AZ31B and hybrid composite. We are planning for hybrid composite. So recently I inquired at Indian Institute of Science also, sir, but they are saying we are looking for metal printer. I think we need metal printer where we can develop the magnesium alloys, magnesium metal matrix composites. So we are planning to use FDM, sir, but I'm not so much thorough. But just I need clarification from your end, sir. Can we go with FDM or any other method?
It is not by additive manufacturing. No? You're talking about a conventional manufacturing route only, right?
No, additive only, sir. Sorry, I'm looking for additive only, sir. Additive manufacturing approach.
Additive, I'm not really sure about whether you go for FDM. So what are the issues there actually in FDM?
Sorry.
What are the issues you are facing in FDM when you're doing it?
No, sir. We didn't try it, sir. We are planning. Actually, we are at the initial stage, sir. Just I'm making a cross verification with all the experts who are working on this area. So just now you give an example, no, sir. AZ31B.
AZ31B, as it AZ31B, I think people are pure AZ31B, they're depositing. But with a composite, I have not come across any papers related to that. AZ31B, pure AZ31B, they have done SLM process, they have done it. DED also, they have done AZ31 actually. But the composites, I have not come across any articles related to that. I'm also not probably expert to comment on what is, can we do it in FDM? Probably I think anybody who's attending it, otherwise next week, you can discuss with this Amit. I think Amit is quite expertise in that, I believe.
What is the advantage, sir, of using a EM rather than a conventional approach while developing composites?
See, one advantage with that is with AM is that you can actually do a functionally graded composite as well. Let's say, as I told, especially when you're doing an DED process, right? So once you have, let's say, I want very, I mean, the way you do it in a carburizing or surface hardening treatments, right? What you do surface hardening is that you want to have a tough core and you have very hard case. Okay? So case should be very hard. So if you're doing a component here, what you can do is actually when you're going towards the top surface of the composite, you can vary the composition of the layer composition, tweak the composition. You make it as a very hard surface, and probably interior you can still have a tougher core. That's what you can do with a DED kind of processes. So that's one advantage which probably it is difficult using a conventional subtractive manufacturing method. Because maintaining that kind of, otherwise you have to use another heat treatment processes or something. First, it works out. When you want to do a solid solution kind of hardening treatment to incorporate in a function gradient along the thickness or something, then it's very difficult. Then you will not be able to do it with a conventional. So that is where probably AM gives you a promising.
Okay, whether any lesser chances, sir, with respect to agglomeration when you go for characterization by using additive manufacturing approach, whether there is a probability will be very less of agglomeration because we are adding
agglomeration part.
agglomeration with respect.
See, no. But since you're printing a laser of very high intensity, you don't see very. You see certain kind of coring or segregation, which you have to eliminate it by heat treatment, post processing heat treatment. That is another challenge. The problem. It's not about agglomeration. I'm talking about. It's most like a coring or segregation.
Okay.
Yeah. So that is one other challenging process, because what exactly happens is that if you take a metal. Let me just give you that example here. So typically what metallurgists do that, probably most of you were aware of this phase diagram, right? So if you are doing it very slowly, you're cooling it. You take about this is a complete liquid. Talk about here, you have a liquid plus some kind of solid, and you have a complete solid here, right? So this is what actually grain structure we're looking about. This is what happens when you're actually cooling it at slowly. So what happens, any grain, if I take it, okay, the composition here and the composition is here are same, because the cooling rates are pretty normal, are usual. The cooling rates here and here are not significantly different. If you take a additively manufactured component, what happens is that because of the differential cooling rates, you will have a region which is higher in concentration, and you will have a region which is in a lower in concentration adjacently. Okay. This is what you have to eliminate by a means of heat treatment process. So all additively manufactured components, you not only heat treat them to reduce the residual stresses, but also you heat treat them to homogenize the composition. This is something people always have to do.
Yes, sir. Thank you, sir. Thank you, sir.
Thank you, sir. Thank you, sir.
afternoon, sir. Okay.
Sure, sir. Hello.
Yes, sir.
Shall we get started?
Yes, sir. Can start, sir.
So thanks. It's wonderful questions. It's good to see that participation from the. I'm also learning something which is new, which is good. So particle and powder bed size, if you look at it, as I told, these are certain parameters I'm talking about: feedstock and base plate. The most important, as I told, apart from the laser parameters, is the particle size and particle distribution, quality of the particle. If you look at typical particle powder size limited by AM process consideration, SLM uses around 10 to 45 microns particle size range, whereas E-beam uses slightly higher because you can control the voltage, you can control the intensity, as some person was asking. You can actually increase the intensity, which actually controls the particle. You can melt the thicker particles as well here. Take a DED slightly thicker because DED also can use at a slightly advanced lasers and so on and so forth. And you can use E-beam as well as laser as well. So if you look at the layer thickness values in SLM layer thickness will be around 10 to 50 microns. Okay, I'm talking about each layer thickness. And the beam diameter is around 75 to 100 micrometer is the beam diameter. Typically, almost 2 times or 5 times you're talking about. So you talk about PBF in a E-beam setup. So layer thickness is around 50 microns. So slightly on the higher end of the SLM. And your beam diameters are typically more intense here. Okay, more intense. That's why it's also so it can melt even thicker and thicker particles. Talk about again DED water with wide fed. You have a different layer thickness, and this you can go for a thicker layers, whereas this you can go for a smaller, slightly less thicker layers in a DED process. But one advantage of DED powder bed compared to these two is that you can actually go slightly thicker. Beam diameters are slightly sharper compared to this and bigger compared to this. And then what you can do is that you can functionally deposit the gradient compositions. That's an advantage of DED. So go back to the powder preparation method. Since we're talking about the powder preparation method, so atomization is the powder preparation method which is most extensively used to make the powders. Okay, what is atomization? Atomization is something like this. You take a liquid, you melt the material, liquid alloy, right? A given composition alloy, TIC or you want to do it, or any alloy you can do it. Is that when you're talking about a stainless steel or any alloy? So you melt it and then you allow it to fall through a small orifice from the ladle. And as soon as it comes here, so you put a very intense gas or fluid here. Okay, atomization, what happens that you're talking about it could be high velocity jet of air, nitrogen, argon, or helium. And what it does is that it actually fragments these droplets water which is penetrating through this orifice. This jet will fragment it to a very fine powders, very fine powders. And these powders are collected in a silo and they're separated. Okay. So what conventionally you do is actually instead of atomization, you cast it. You're not casting it here, you're melting it, but you're making these powders and then you're fragmenting it to very fine particle. So this velocity of jet could be a gas. In the case of gas, it could be nitrogen, argon, or helium. It could be water as well. Sometimes actually use water, high impinge water can use it. And sometimes this is what actually water jet, the people use it here, the water jet process. This is where the particles are connected. And sometimes you use a plasma atomization as well, okay, which is slightly much more expensive. So if we look at the typical particle size distribution compared to these two, okay, these are the water jet atomized particles and these are the gas atomized particles. Okay, very randomly non-uniform. There is no spherosity at all here. Particles are pretty randomly distributed. Okay, and whereas you look at here, particles are slightly rounded shape. Okay, this is what actually you get with the gas atomization. And what you can see is that some particles are still irregularly shaped. This is not a sphere or something. Okay, and then again there are some particles which are actually unable to separate, and you can see there is certain surface roughness associated with these particles. Okay? Particles are quite to suffer, but the quality of the particles is much better than the water atomized particles. Look at the quality of the particles here. So this is the gas atomized particles. I'm doing a 2D image of this here. You see these are the porosity that got entrapped due to the gas entrapment. Okay, gas entrapment leads to this porosity in the particles get translated to the final product as well. Okay, that's why. So these, what are the porosities you see in additively manufactured components? So one of the source could be this powder, the porosity of the powder itself. Okay, and these are called as satellites. Typically, the name itself indicates the satellites get stuck to the particles, bigger particles during the atomization. So this is called rotary atomization. In rotary atomization is that you are trying to rotate it, and then you are still using a gas as the atomizer. So it is a non-spherical. Some particles are long, and then you still see very small porosity here. Okay, but still surface finish is slightly bigger here because you're using a rotary kind of atomization. The best atomization powders, what you get is the plasma atomization. Okay, plasma atomization, you get very, very rounded particles, fantastically rounded particles. And then you see that most of them are actually have a uniform size. Okay, with no porosity, less porosity or no porosity. At least this image shows that there is no porosity, but you cannot claim that based on this particular image that there is no porosity. The porosity is very less. And because of this, what happens that becomes very flowability is very good. When the flowability is good, the particles easily flow through the hose, and then they can actually also have a good bonding ability between them. That's very important. Okay, so the plasma atomization gives you the best powder quality. That's why these powders are also expensive. In fact, I mean, these powders, if you look at the price of the powders, I think half a kg or 2 kg, I bought it around for 25,000 rupees or something. Okay, the other ones, not these ones, the other ones. So beam powder interactions. The interaction of the heat source with the feedstock or melt pool can lead to substantial liquid metal ejection. So the porosity sources, as I told, one source could be the powder particle itself, the gas atomization process it actually comes. So other is the interaction between the liquid metal and the porosity. As actually somebody is asking, a person was asking, so whether laser heats up, how the intensity looks like or something. Okay, sometimes your laser power is very strong. It actually ejects certain particles as well. Okay, so it's particle and actually it leads to porosity formation as well. Okay, so that's one thing. And this pattern rejection, actually there is a convection transfer that happens with the liquid and metal pore. And laser impacts the high energy and the powder bed via photons, and therefore absorptivity or reflectivity of the powder material is actually an important parameter that decides the laser intensity. That's what the laser intensity, as we're talking about. So what is the bed thickness and what is the powder material size? These are the ones which actually dictates the laser intensity you're talking about. And particle size distribution determines the key laser power. Smoking, and these are the one talking about SLM. When you do about E-beam, there is a term called smoking. So where if you're using since E-beam, you're using a high impinge, electrons are impinging on the sample surface, and there is an electron transfer that takes place between the beam as well as the sample. Okay, so what actually does is that it leads to a kind of bulk displacement of the powder. It's also known as smoking. So this is what exactly happens. Okay, this is an electron beam which is actually passing through the material, and if you look at this region, this is initially, and actually gets completely smoked out. Okay, it's called as smoking. Smoking is also not a good thing because it actually leads to certain kind of defects in the additively manufactured product. Okay, so it's aerostatic repulsion. So these are some of the beam powder interactions which also leads to certain kind of porosity. Yeah, so coming to here, so this is what, if you look at any additively manufactured product, Okay, you take make it and then look at the microstructure here, and you see a small pores, you see a large pores. Okay, the small pores are actually low energy and lack of fusion. Otherwise, these small pores are actually coming from the particle quality, and these are coming from the lack of fusion. If the particles are not, if the laser power intensity is not good, if the the temperature flow is not uniform, then it leads to certain kind of defects. Okay, with keyhole formation, lack of fusion. Okay, so this is what actually the process induced porosity. Sometimes the process induced porosity is always spherical, whereas the other porosity that happens during the solidification, that leads to this kind of shrinkage porosity as well. The bigger ones, the much bigger ones leads to are developed due to the shrinkage that happens between the successive layers. Okay, not filling the intricate area, that is actually hard to. Okay, this is one example of that. Okay, this is actually keyhole induced porosity is one example of the shrinkage porosity that is developed during solidification. As I told, since you're talking about one layer on the other, layer by layer, so there is always the temperature gradient between this layer to this layer as well. It leads to some kind of differential solidification shrinkage and leads to certain kind of cracking or porosity in the sample itself. That's one of the reasons for you see a bigger porosity and so also. Okay, so basically. So scan strategy. We're talking about scan strategy before. And scan strategy is very important factor in additively manufactured products. We'll see in the subsequent slide how does the scan strategy influences the microstructure. So what happens is that there are certain strategy that you can use it. So if you're talking about a laser here, and this is your component, you travel once like this. This is called as unidirectional fill, and this is the bidirectional fill, and this is called as island scanning. Okay, island scanning is that you divide the entire square into multiple squares, and then you adopt multiple scanning like this. Okay, so that each of them are 90 degree or some degree apart from each other. Okay, this is one of the scan strategy we employ to develop a island scanning. This is called as you're dividing the entire area into small islands, and you're scanning these regions to get a more homogeneous microstructure. What you can avoid is that you can minimize the thermal stresses by this method. Okay, you're using it. So this temperature is more or less same, because the moment laser comes from here to here, the temperature difference will be significantly higher from here to here. So what you're doing is that you're actually miniaturizing that and then trying to minimize the shrinkage or the temperature induced stresses in this around this area. Okay, scan strategy and scan speed. Okay, the scan speed affects both porosity and microstructure. We will see that in the subsequent slides. Scan strategy, if you look at it here, so I'm talking about scan strategies, various scan strategies and scan speeds. Okay, this is the scan speed, very high speed and alternating, it leads to a very high porosity, and very low speed and alternating also. Alternating is typically avoided actually. Okay, alternating scan strategy is always avoided. So whenever you do that, one advantage is that do you pre-sinter of the particles. Okay, before putting the particles inside the water bed, you pre-sinter them and then actually put inside the bed, so you get a better without any porosity. That's what I'm going to say. So at a low scan speeds always gives you a better what is the word, product with less porosity. Okay, this is what actually overlap and pre-sinter, and this is what actually somebody says that. And other is the delamination cracking. So if you're exactly, we're talking about one question has come up is that a person was asking about so what could be the optimum layer thickness? Okay, what could be the laser intensity? Okay, if your laser intensity is low and your powder thickness is significantly high, right? What it does is that it cannot melt these layers. Okay, so what I'm told, powder layer should be commensurate with the laser intensity, what is the power what you're using for the additively manufactured product. Right? If they are not concomitant to each other, then what you're going to end up in that you're going to end up in incomplete melting of the powder layers. Incomplete melting of the powder layers leads to certain kind of cracking at the junctions. Okay, this is one layer and this is one layer, and the material is actually cracked between these two. Okay? So that is a delamination. That's a completely it gets delaminated. Okay. So another thing is the solidification crack. Solidification cracking, as I told before, that if you have wide mushy zone is typically what I'm talking about is that if you're trying to do certain alloying elements, let's say this is one particular material, okay, and I take another, this is a narrow mushy zone. This is called as mushy zone. And if you have a material which has another okay, let's just do that. Okay, so this is a wide mushy zone. Okay. If the liquidescence, this is a liquidescence, this is solidus, this region is pretty significant. That actually called as wide mushy zone materials. So large liquidous lines. So especially inclinal 718, these kind of super alloys. So in that case, what happens is that there is a solidification shrinkage. The moment this guy gets cooled and this guy some part is still in liquid state. Okay. So in that case, what happens is that you tend to see this kind of solidification crack. Okay. And again, large thermal contraction, because you're talking about aluminum alloys, especially you have a high coefficient of thermal expansion for these alloys. So there is a large thermal contraction between the one layer to other layers that also leads to some kind of solidification crack. Okay, and large melt pool in titanium, especially large solidification shrinkage like this. So you have a for titanium alloys. These are the typical cracking you see in this. Okay, long crack, short cracks, and these cracks. Okay, these are actually again happens between the layers again. This somehow you have to work out. I think the one thing is that what is the you minimize the powder layer thickness so that you can minimize this. So what I'm talking about is if you're using Incoron diagonate is 30 microns. So you cannot use the same thickness for aluminum alloys. You cannot use the same thickness for titanium alloys. The thickness of the layer depends on what kind of alloy system you're using one, and what is the laser power you're using. That also is another important. Okay. So when we talk about metals and alloys for AM, I think this list is not exhaustive. There are not a lot of additions are coming here now. So these are, if you take a commercially alloys using metallic alloys, I'm talking about here, and stainless steels, titanium alloys, aluminum alloys, nickel-based super alloys, tool steels, and cobalt chromium alloys, all are manufactured through powder bed fusion. Okay. When I say titanium alloys, so I am sure Ti-6-4 is very popularly made now actually, and we are trying to look at some alloy Ti-6242, which has some niobium and other fancy elements are there, and which is not available core. Actually, they are able to make it in India. I think we're trying to get it from abroad. And then again, this is actually even then they are also optimizing the process parameters, because again they have to make the alloy and then they have to atomize this composition and look at the powder particle size and powder particle composition distribution, and then only they can be able to sell it as a something. Okay, aluminum alloys. Many of the aluminum alloys are actually made through PBF now, a powder bed fusion. Nickel-based super alloys, I think IN 718. When I say super alloys, not all the N8 Gamma super alloys. It will be some compositions are being made already. And tool steels and cobalt chromium steels are all made actually. Okay, and these are the processes by which all these alloys can be made: bandage and paging, DED, and PBF, and so on. But the sheet metal delamination, these are still these three are the ones which are actually more popularly made it actually. Look at the microstructure. We are talking about the microstructures in the beginning. So when I told started with our rod processing alloys, so all the engineers want, whenever the additively manufactured component, if you make it, the objective is how this guy additively manufactured product fares with respect to the rod product. Okay, how the microstructural differences between these two. Okay, for example, I tried to put it a couple of microstructure comparison microstructure here. So it is an IN 718. This is an Incoron based 718 alloy, and this is a cast material, conventionally cast material, and this is a selectively laser melted. Okay, without any rod processing, the as cast structure, the microstructure looks like this. There is a delta phase, There is a carbonhydrates and there is a grain boundary. Okay. Look at the AM components. AM components, the delta phase is much more dispersed here. And the grain boundaries are also much more finer. For instance, the grain size is pretty small in that case, actually. And then within grain, you don't have any delta phases here, whereas the grain delta phase also appears in the grain, which is good or bad. That once you do the experiments and understand the high temperature properties and free properties, then only you're able to see. Apparently, what I found is that the AN718 SLM sometimes outperforms the conventional as cost LM. Okay, in terms of, because this delta what got distributed within the grains will also give you certain beneficial properties for 718 material, which is why actually 718 is very widely widely uh, made additively manufactured alloy. Okay, that is something which is. So look at this. This is what actually this because 718 is also used in cast condition. That is why we are comparing the cast condition of 718 and SLM. Okay. Look at the Ti64. Okay. Ti64 is a titanium, 6 aluminum, and 4 vanadium. This is widely used aerospace materials because of its high specific strength. Because the density of this material is around 4.5, the strength is around 100,000 gigapascals. Okay. So strength by density will give you the specific strength. The specific strength of this material is very good. Look at the wrought alloys and SLM alloys. So what you see in the wrought alloys is that you see a proper grains, okay, and there are certain kind of lamellar structure, which what you don't see in the additively manufactured Ti64 alloy, SLM process Ti64 alloy. You see very fine distributed phases here. We'll see subsequent slides. I have much more work to present on this. So what is talking about, you see a very fine acicular microstructure here. Okay, SLM process because of the fast rapid cooling rates. What happens is that because of the rapid cooling rates, you're talking about 10 power 5 K per second. You're talking about 10 per second. Okay, because of this, so you actually create some kind of non-equilibrium phases. Equilibrium phases. Non-equilibrium phases, you see that. Okay, which is sometimes beneficial for the string, very bad news for ductility or toughness. Okay. And this again the cobalt chromium moly, which is also an alloy, which is additively manufactured in wrought process. In wrought process, you see a slightly bigger grain size than the EBM processed cobalt chrome moly. And then the grains is very small, very fine. This is called as coarse grains. Okay. Sometimes you want to have a creep properties. This is a bad news. Creep is good. Strength, this is good. This is bad. Okay. Look about Ti6. This is 17.4 pH. 17.4 pH is a precipitation hardened stainless steel. And look at again here also wrought product and cast product. You see a kind of difference in the microstructure. Okay. You see a lot of ingredients and small microstructural features which you don't see in the wrought process. Okay. Again, same aluminum alloy. And this is S13 tool steel, and you have a 316 alloy. 316L is a stainless steel, extra low carbon stainless steel. Okay, and again you see a very good homogeneous microstructure here. You see very, dispersed microstructure here, and then the strength is good, but toughness and other properties are inferior to SLM process ones. That is the reason I think people always use some kind of heat treatment processes to stabilize that to find out microstructure, which is actually gives more properties which are close to the conventional cast alloys also. Okay, this is one example I'm trying to put it for ASI steel. It's a low carbon steel. So you look at this is a cast material, and this is a forged material, and this is a this is a cast material. This is additively manufactured. This is additively manufactured material, SLM, I think. SLM, and this is a cast material. If you look at it, if you look at the additively manufactured, you see this kind of fish scale structure here, right? And which are pretty heterogeneous here, right? Some grains are bigger, some grains are smaller, and they are interpenetrated into each other. When you look at the same here, you see a very homogeneous microstructure here. Okay, in broad product. In cast, you see a very big microstructure. Okay, look at the properties here. So cast material, because the coarse grains, it actually exhibits a good ductility, almost 60% you're talking about, but low strength. Whereas in forged materials, you see a lower yield strength but good tensile strength, and then have a strength almost it is slightly lower, because as the strength goes up, the ductility comes down. So additively manufactured product, you still see a very good strength, and the ductility is almost half of it. Right? So what I'm saying is, whenever you see the strength is the most important criteria and ductility doesn't make a good engineering design parameter, you don't want it to be good engineering parameter. I think additively manufactured alloys will do much better job than the as casted forged, because the microstructure you see a slightly stain hardening behavior here, which is don't you see that in the AM alloy. 17.4 pH steel, as I told here. So you're talking about three comparisons here. Okay, this is the cast material, and this is a hot isostatic pressed material, and this is the SLM process material. Okay, this is a cast, and this is a powder metallurgy route, and this is a additively manufactured route. Okay, if you look at it here, so what you see is that the SLM processed ones gives the best strength. Strength is very good, tensile strength, and yield strength is also much better for this, unlike your previous case, ASA steel case. Okay, so whereas it exhibit a good, but ductility is again it's a problem here as well. Okay, if we look at the XRD pattern of these three materials, this is SLM, HIP, and as cast, and you see that as cast will have a more 111 intense peaks compared to these two. Okay, which shows that there is certain kind of preferred orientation there in this material texture or there in the material. Talk about aluminum alloys. In aluminum alloys, you have aluminum alloys as deposited, and this is the after heat treatment. Okay, these are the as deposited ones. We look at the ultimate tensile strength and versus elongation. I'm trying to plot it. Okay, very few alloys exhibits around a 30% strength, 30% elongation. Most of the alloys will have less than 10% elongation. Okay, so once you heat treat this after SLM process or additively manufactured process of 3D printing, what happens is that you are trying to push the most of the segments towards the more than 15% or so. Okay, what happens is that the post heat treatment of the aluminum alloys is found to be an effective method to increase the ductility of additively manufactured products. Okay, since you cannot do any operations on this material like what you can do with the conventional alloys, what you talk about processing maps, you don't have this for this rod processing maps. So, but the only way you can actually tweak the microstructure is that by tweaking the heat treatment cycle. Okay, again, that itself is so many parameters are there. Okay, what is the temperature you have to heat it? What is the rate of cooling? So that has to be proper study in that. So that's the reason I think a lot of nowadays people are using a lot of machine learning techniques to optimize the processing parameters for additively manufactured products. This is actually another booming area, in fact. And if any of your students, mechanical engineering students who are interested in machine learning, applying machine learning, and this is a very challenging area here, and a lot of challenges are also there. I think it actually gives them good experience as well. Okay. Yeah, Ti6 alloys. If you look at the titanium and 6 aluminum 4 and vanadium alloys, so this is what I'm talking about. Ti6 alloys. So titanium is a HCP structure at room temperature, and BCC at high temperature. High temperature means above 882 degrees centigrade. What you can do is actually this is the high temperature. You cannot do it in high temp. This is actually always available at high temperature. This is available at room temperature. You add certain alloying elements like vanadium to bring down this alpha and beta both together at room temperature. Okay, what vanadium beta stabilizer. So what as a result, what you see is that if you look at raw Ti6 alloys, you can actually retain both BCC phase plus HCP phase at room temperatures. Okay. So this has certain advantages and this has certain advantages. This has very high corrosion resistance. This is very high creep resistance and ductility. Okay. So we want to have, generally if you take a pure titanium is always at room temperature, it is in this phase, high temperature in this phase. The moment you add aluminum and vanadium to that, so what happens is that you can retain both alpha plus beta at room temperature, okay, which is actually gives the best of both properties. If you look at the Ti6 for alloy, look at wrought Ti6 for alloy and cast Ti6 for alloy, cast will have certain like this. These are called as prior beta boundaries. And these are certain latch structure that you see in a cast structure and the cast Ti6. After cast, you process that using processing maps, as I told you before. What you get is you get a very uniform grain size structure with a alpha phase and alpha plus beta phase. That's what you get it here. Okay. If you do that in a additively manufactured, you don't have this facility of processing them from the cast structure. You only have to live with the cast structure. Look at the microstructure. None of the microstructure is similar to wrought alloys. Okay. This is a problem with, I'm not saying this is a problem. Generally, the aerospace engineers, the moment you go there, they don't trust the additively manufacturing yet for complicated applications or complicated, complex parts, because their microstructures are not similar. Okay, immediately they'll thrash you that this is not we cannot use it in the engineering application unless it is actually has to be tested in real life, right? So this is what actually you see very sharp lines here, which you don't see in any of these microstructures. Okay, these sharp lines. These are all non-equilibrium alpha phase, alpha point phase. Okay, that's what. So more or less everything has similar microstructure here. So what we can do is that since you get microstructure like this in island scan in a one scanning, alternate scanning or uniform scanning. So what happens to these microstructures if you employ this kind of island scanning? This is what actually we have done this. Okay. So what we've done is actually again, as I told, we have fragmented this entire area into small fragments. Okay. And then used island scanning in these regions. Okay. There are two types of scanning so used. We have varied the scan rotation as 90 and scan rotation as 67. Scan rotation 90 means alternate layers are 90, whereas scan rotation 90 means you are slightly rotating it by 67. One layer to other layer, you're rotating it actually. Okay, this number is very important number. What exactly happens, people found out this number you see very often in many of the AM literature. This happens to be whenever you rotate by 360 degrees centigrade, the minimum, the next odd number compared to 60, 67, above 67. So this gives you the highest degrees of what is that isotropy in terms of the properties. Okay, 67 degrees. So that's why people use this scan rotation quite often in AM process. So look at the microstructure here. So I want you to make a cut on this. Okay, this is a microstructure using by SLM, using a traditional one-line scanning. Okay, zigzag scanning or something, zigzag scanning. But if you do island scanning, you see a completely different microstructure. Okay, this we don't call as, I mean, it is a microstructure, but to differentiate from this to that, we call it a mesostructure here. What you can do is actually you can create a small blocks here. Each block exhibits a different orientation, different grains. Okay, so this is what we have varied 90 degrees scan rotation, as we were talking about before. So this is B3090. So 3090 means 30 microns is the layer thickness and size the 90 degrees is the orientation. Okay. And you take another grain like this, so structure like this. This is B6067 or 3067, sorry, where T is 30 microns and size 67 degrees. Okay, by just slightly, number one, by tweaking the island scanning, you are homogenizing more or less the microstructure, which is not possible here. Okay. Number two, what you are doing is that you are creating by just varying the scan orientation without changing the layer thickness. You are completely differently getting a different microstructure. This is actually is a more homogeneous microstructure. equiaxed microstructure. Sorry, equiaxed microstructure. Okay, this is very unique microstructure. So this microstructure is similar to, or more or less similar to, what people do is in a conventional rod processing ones, because you're controlling the flow of heat and as well as the anisotropy between the two layers and so on and so forth. Okay, this I'm talking about the build layer. This is actually called as build direction, and this is the scan direction. And scan direction, you see a completely again a different the microstructure here is different from the microstructure here when you're building it actually. The properties sometimes could be different. If you're testing a sample in this direction, and if you're testing a sample in this direction, the properties of this material could be different because of the differences in the microstructure. What you see here is that you see these kind of features which are actually non-equilibrium microstructures. Okay, non-equilibrium phases, which is called as alpha prime, which is good sometimes because it gives you very high strength. Okay, if you look at this is the B component. Okay, this is a build direction. B stands for build direction, S stands for scan direction. If you look at the build direction is giving almost 1000 megapascals, almost 1 gigapascals of strength. All materials exhibit more than 1 gigapascals. Okay, and look at the ductility is pretty poor. Ductility titanium wrought alloys, you take it, it gives you around greater than 30%, whereas ductility is very poor here. It's around for 13%, 14%. But what you can see is the fracture toughness, K1C. K1C fracture toughness values, you get very good values. I mean, if you look at typical K1C values for rod process will be of the order of 60 ampere root meter. That is also the same term. Okay. So what I'm talking about is that most of the studies you see that. So these alloys, what are made by these conventional manufacturing methods, rod processing methods, the microstructure of these AM alloys can be varied or tweaked in such a way they will be close to conventional microstructures. Okay, rod process microstructures by varying the island kind of scanning as well as the scan rotation, which is 67 degrees. And also by proper heat treatment, post-processing treatment, it is possible to increase as well. We have not done any post-processing, but it is possible you can actually increase as well. Okay, so we did something study on high strain rate deformation. We wanted to look at, because these are the alloys which are used in aerospace applications like landing gears and all. So they experience a lot of dynamic loads, high strain rate loads, and we wanted to look at how these guys perform with respect to the dynamic loads, the deformation at high rates, how stronger they are at impact loading conditions, is what we wanted to look at it. And what we have seen is that, okay, if you look at it, this one, okay, these three figures, these are the wrought alloys, wrought Ti64. Okay, these are the various Ti64 used by DED, LDAM, EBM, and so on and so forth. Look at SLM1s. SLM1s are almost exhibiting a much higher strength compared to this, any of this. Strength wise, no question at all. AM actually materials exhibit a very high strength because of the non-equilibrium alpha pi precipitates also. Then so this is actually talking about, but ductility is still an issue. Ductility is still an issue. Okay, I'll take some questions here and we'll go to the last topic of today. What limits the use of AM in critical engineering application? Okay. Any questions?
Dear participants, please you can unmute your mic and ask. starting from the first slide, we could see a very different orientation towards the microstructures.
Thank you. Thank you. Thank you, sir.
I think there is no query, sir. Shall we continue?
Yeah. So I'll present the last couple of slides, probably on the what limits the usage of AM applications in critical engineering applications. Okay. So this is recently there was a case study that has been done in a BES, a French agency, okay, on hub failure made of Ti64. As I told, this Ti64 is typically made of hub which actually undergoes a dynamic impact loading conditions, as I told, right? So this is the component that's failed. So this flight is going from, I think, France to Canada, and this incident happened immediately after 1 hour. And despite this, actually traveled for 3 hours and died in Canada, okay, without any major damage. But by the time it actually went to Canada, this is how the engine part looked like. Okay, it actually completely one part has come and then it broke all the turbine blades. Actually, you look at this turbine blades, what you see, it will broke all the blades. So what actually people had done is that they tried to investigate. As I told, whenever we do that, we wanted to investigate what is the failure mechanism and why it is failed. So what we realize is that what this company has analyzed the failure analysis of this, and then they found out that one certain region where it looked like the crack has initiated here and propagated here. Probably yesterday with Professor Jayakanthan's lectures, you would have seen that fatigue fracture of additively manufactured alloys, especially with the focus talk on that, where he would have presented a lot of microstructures about the fatigue failure features. Okay, fatigue failures, we all know that it is a repeated material fails under repeated cyclic loading conditions, right? So it could be well below the yield stress, number one, right? And there are two salient features of a fatigue. One is the striations. The striations you see on the microstructure, that is called fatigue. Otherwise, you'd see a crack here and actually it goes, it takes an initiation and it actually goes, it's a ratchet mechanism or something. Okay. This is how the crack would have initiated here, it would have propagated here. That's how it looks like. When you look at it actually. So see that here. So what people have done is actually they have done some kind of microstructure analysis. As I told, as long as everything is going fine, nobody cares about microstructure, but some failure happens the moment people dig deeper into the materials issues only. Okay, because most of the failure that happen because of some uncertainty in the materials and so on and so forth. And look at this here. So this is actually done by analysis done by Pratt and Whitney, which is released, which is actually openly available here. And what you can see is that you can see a very clear serrations here. Okay, these serrations part you can see here. Probably yesterday would have seen this a lot of images like this. These serrations are these are the fatigue serrations. Okay, striations. Sorry, striations. Okay, and then what they figured out is that they couldn't able to even notice also from this, and they have done a technique called as elemental mapping. This is called as elemental mapping is a technique that is used in XRD and with a EBSD, which is called the electron backscatter diffraction spectroscopy. What they have done is actually they have seen this kind of very localized regions. Okay. This is called as microtexture regions. Microtexture regions. So what they found is that these regions are the ones where all the alpha prime or one particular phase is actually getting dominated. Okay, and then they found out is that these microstructure regions are responsible for that. So they started with some microstructure in the beginning as a rod processed one, and then during the fatigue cycle, since because of there is a lot of texturing that happens, a lot of coagulation of single phase happen during the material transformation or whatnot. So that led to this kind of abrupt failure is what they found out. This is called as cold well fatigue. Cold well fatigue, you know that actually because the material actually goes from high temperature to low temperature subsequently, and then leads to kind of microtexture regions. Okay, these microtexture regions are the reasons for this premature failure of the material or engine or hub. Okay, that's what they found out is. What I want to say is that this wrought alloy has been commercially used from 1960s onwards. Okay, It's almost 60 years or more than 60 years. Even now, people are unable to understand certain aspects of these wrought alloys, which is well-tested material. Okay. And then the moment you go to the aerospace alloys and they say that, okay, I process this Ti64 using additively manufactured process, can you use that? I mean, the immediate answer is no, right? Because they say that, okay, you show us what is best in that. Okay, you do it all kind of testing methods. I mean, you do the components. That is the reason laboratory scaling helps you a lot, because you take a wrought alloy and you take a cast alloy and do it laboratory scale testing and do it a component level testing as well. Take a component of this, take a component of this for the same cycles you test it. Cut the microstructure, look at the microstructure regions and see what are the changes that are taking place for this to that, and then only you'll be able to convince the end users properly so that they can be used. The easiest thing is that's why used in non-critical applications where these are used, and show them that these materials perform better than that, then the trust actually slowly builds up. Okay. Yeah. So AM still is a promising and viable manufacturing techniques to produce. As I told, I think it's a very promising technique. And sometimes rapid cooling often results in undesirable microstructures. Okay. And then sometimes to defects, which actually needs to be addressed. That's another important aspect in front of all the engineers and scientists who are working in additive manufacturing. So it is important to develop a processing map kind of analogy or methodology for AM alloys, the way we have done it for wrought alloys. What is the temperature? What is the strain rate that material has to be processed to get an optimized microstructure? Similarly, what kind of laser intensity? I was talking about, somebody was asking as well, Dr. Prasanna, I think. What laser should be used? What is the laser intensity? Okay, what is the powder bed thickness? Okay, for this powder bed thickness, what should be the laser should be used? Okay, for this alloy, what should be the laser should be used? Okay, those things has to be clearly spelled out. Then only people you can say that you have a good understanding about the process. Okay, and have a better understanding about the microstructure and texture as well. Texture I didn't stress upon much here because it's again a different lecture, one or lecture needs. So very little understanding of texture evolution, very little understanding. If somebody is working in texture of AM alloys, I mean, there is no understanding at all. In fact, not many studies. So everybody is running towards understanding this. And then, yeah, use of critical engineering applications still elusive. So that is the reason I think we wanted to have use it for non-critical applications and then test them, and then use it for a critical applications. And large data is available, and some efforts need to be addressed to understand interpretation of the data. As I told, actually, techniques like machine learning methods and data analytics, now every student is wanted to have a job and then want to work in AI and ML. So rather than actually digging a different problem, I think we can actually ask them to work on appropriate problems in AM alloys. Okay, with the existing literature itself, what are the available literature? Give some certain problems to them and come up with certain methods which actually will give you what are the optimized processing parameters. Okay, some of the students here also working in the similar areas that they will be looking at the microstructures from different papers and what are the different process parameters, and they'll feed that microstructure into the ML models, machine learning models, and train them and change the process parameters and then see what kind of microstructures you can get at the end of the method. Okay, because nowadays you can actually ML can do that. ML can predict once you train the system using certain machine learning methods, it actually can predict certain microstructures. This is another thing probably a lot of engineers has to work on right now, so that we can actually take it much faster or something like that. Okay. Thanks very much for your patience, and I would happy to have any questions from you. If not, actually, you can also reach me on this email ID, ishwar@iiti.ac.in. Okay, if you need, actually, we can also discuss there as well. Okay, thank you.
Thank you, sir, for a very informative session.
Thank you, Shekhar.
As a key takeaway, we would encourage the students to work on the ANAML for analyzing various data regarding microstructures. Surely it was a very wonderful session, sir. Thanks a lot once again from BITM Bellary. We look forward for any other avenues, sir. Thank you, sir.
Absolutely. Anyway, if somebody wants to work on, because we have good experimental setups for high strain rate deformation and all. somebody wants to do some experiments or somebody wants to work on this, please feel free to write to us. No problem, we'll be able to help you. And we have some good experimental characterization techniques as well here. If you want to do EBSD or SEM and everything, feel free to write to us. I think we'll be able to help whatever the best we can actually. No problem at all.
Sure, sir. Sure, sir. Thank you.
Yeah, we're happy to collaborate and we're happy to share our facilities as well.
Thank you. Thanks a lot, sir.
Yeah,
Thank you, sir.
thanks a lot. Appreciate it. Thanks a lot.
Thank you very much, sir. Thank you.
Yeah, thanks a lot. Thanks a lot, sir. Thanks.
Dear participants, we have an announcement. The tomorrow's session is postponed to day after tomorrow, 5 o'clock, because of the non-availability of the sir. Sir has given a schedule on day after tomorrow. So tomorrow there will be no sessions. So the tomorrow session is carried forward to the day after tomorrow. So we'll just put up all the details to your mail. Thank you. Thank you, participants. Thank you, sir.